right. Good afternoon, everyone. Good to see you all. We're going to do some more networking today. And format for today is going to be like last week. So first half of the lecture, going to be a speed run to teach you a bunch of stuff about how the internet works. Then I'll talk a little bit about security as we go. And then the second half of the lecture, we'll talk about using cryptography to secure network communications. Yep. Apologize if I am a little low energy today. I'm kind of under the weather. Nothing contagious, but just you might get to supply the energy for me today. Sorry. All right. So we talked last time about low-level networking protocols, especially like local area network stuff like ARP and DHCP and how they can be attacked. And what I want to talk about today is about wide area network protocols. BGP, which is a routing protocol, which is how do my packets get to Amazon? How do they find their way to Amazon servers? TCP, which is about how to make sure that my data is transmitted reliably over the internet when the low-level IP protocol is not reliable, and UDP, which is an alternative to TCP. So let me start with BGP. BGP is about routing. It's about when I want to send a packet, how do the routers figure out which wires the packet should go over to get to the eventual destination? So just as a reminder, everything on the internet uses the IP protocol, and the IP protocol has a way to send packets. And each packet has a source address and a destination address. Those are IP addresses. They're 32-bit value with IPv4, or version 6, they're 128-bit value. I'm going to just talk about IPv4 because it's a little bit simpler, but really IPv6 is very, very similar. And the IP addresses are unique. Every machine has a different IP address. But it's not just an arbitrary address. It contains some information that will help the routers know how to get packets to that IP address. So a router can look at an IP address and has some idea about where to send data so that it'll eventually reach that IP address, which is kind of like the address, mailing address on an envelope. It has your name, which is like semi-unique, but it also has like your mailing address, which is like gives the postal carrier some information about how to get the envelope to your house. Okay, same deal. In a IP machines are grouped into subnets. A subnet is kind of like a local area network. A subnet is a collection of IP addresses. And the format of an IP address, the first n bits identify the subnet, and then the remaining 32 minus n bits identify the machine within that subnet. Okay? So you can think of the internet as like a collection of lots of local networks. And you could think of each subnet as like a local network. Given an IP address, you can split it into the first part, which is the subnet identifier, and the rest, which is the identifier of the machine, the host. The thing is that split isn't always the same. Sometimes it's 16 bits for the subnet, sometimes it's 24 bits, sometimes it's 22 bits. So just a little bit of notation, I'm going to write, to identify a subnet, I'm going to put all zeros in the machine part of the IP address, and then put a slash, and then indicate the number of bits, that is, how many bits are for the subnet. So 128.32.00 means the first 16 bits of this IP address identify the subnet, the last 16 bits identify the machine. Which of those four numbers up there identify the subnet? One 128.32.0.0. Which of those identify the subnet? Oh, maybe I need to give you a reminder about what does it mean when we write an IP address with these dots. 32-bit IP address is 4 bytes, right? 4 times 8 is 32, so it's 4 bytes. So what we do is we break up the 32 bits into 4 bytes. Each byte is a number between 0 and 255. We write down the number of each byte and we put a dot, a period in between them to separate them. You could say that 128.32.0.0 you could think of as an IP address, and the first 16 bits of that identifies the subnet. But that's reasonable. It's perfectly reasonable. It's another way to say it. You could also say 128.32.0.0/16 identifies a subnet. So the numbers for the subnet, is 120 a subnet or a machine? Is it a subnet? Subnet. The 32, is that the subnet identifier or machine identifier? Subnet? Yeah. The 0, the third one, is that a subnet identifier or a machine identifier? Machine. And then the last 0, is that a subnet identifier or a machine? Machine. First 16 in this case are the subnet. You can tell that because there's a /16. If that had written /24, what would be different? Yeah? Then the third byte would also be part of the subnet. So you can think of this as a subnet is like there's some wildcards. It's 128, all the IP addresses of all the hosts in that subnet will have an IP address that starts with 128.32 and then contains something. Yeah. Yeah, life would be simplest if all our subnets were 16 bits and then that leaves 16 bits for the machine. But it's not. It's not. Some of them are 24 bits for the subnet. Like what happened is historically we started out with subnets actually being 8 bits. So you could have 256 subnets in the world. And like MIT got one of them and Stanford got one of them. And I think maybe Berkeley got one of them at one point. And we started handing these out, and then we realized, oh no, there's more than 256 organizations in the world that would like to be part of the internet. We better not we need more than 256 subnets. How about we use the first 16 bits to denote the subnet? And so then, the University of Oklahoma can get one, and the University of Texas can get one. Except we've got this problem that MIT already has a /8 subnet, like it was 8.star.star.star was MIT. So any IP address that starts with 8.star.star.star is MIT, is a part of this like /8 subnet. But if it starts with like 9, then it might be part of a /16. So like 9.3 might be part of a /16. So not all subnets are the same like size on the internet. It's just weird and confusing. You can think of it as like there's some large organizations that have need a lot of IP addresses because they have a lot of people, a lot of machines, and there's some small organizations that need very few, and so that we don't run out of address space. The small organizations, if I had a /16 subnet and a /24 subnet, which would I give to the small and which would I give to the large?
Like small.
Yeah.
Oh, I've got a tiny organization that's got 5 employees, and I've got a large organization that's got thousands of employees, and I've got a /16 subnet and a /24 subnet. Which one does the small? Okay, so which do I give the /16 to? Give the /16 to the large organization because that leaves room for 16 bits for the machine identifier. The large organization have up to 2 to the 16 different machines in their network. And the small organization, I gave the /24, they get 8 bits for the machine identifier. They can have up to 2 to the 8 machines on their subnet. Yeah. This is not important. I'm sorry. I just like went into gory detail on this stuff, which is not a big deal. But I guess I'm teaching you everything. All right. So the internet you can think of as a collection of these subnets, thousands of them. And routers know about all the subnets. And they know the connectivity between the subnets. Each router is connected to one or, well, maybe 2 or 3 subnets. And it knows about all the machines in the subnets it's connected to. So like a router for Berkeley knows about all the machines in the Berkeley subnet. But it probably doesn't know about all the machines at University of Oklahoma. It knows that there is a subnet for University of Oklahoma, but doesn't know anything about the machines inside that subnet. Okay, so to send a packet, how does a packet get to the destination? How do the machines figure out how to pass on a packet so that it'll reach the eventual destination? The way it works is when my laptop sends an IP packet, we check whether the destination IP is on the same like subnet, same local area network. If it is on the same subnet, then we're like connected by, I don't know, Wi-Fi or Ethernet or some local area network. And my laptop will use ARP to ask, hey, I know you're on the same subnet with me. I'm looking for the MAC address, like the Ethernet address for this IP address. Could you tell me if that's you? So I look up, my laptop looks up the Ethernet address corresponding to that IP address and then sends an Ethernet packet on the local subnet to that machine. Great. If we're on the same subnet, it's easy. We don't need any routers. We don't need help from any routers. ARP solves the problem. But what if my machine wants to send a packet to an IP address that's not on the local subnet? Then what it does is my laptop says, I don't know. Not my job, that's the router's job. And sends the packet to the gateway router. Remember when your machine connects to a network? Use DHCP to get some configuration information. And a key part of that configuration information is, what is the address of the gateway router? That's where all packets will be sent if they're not for the local subnet. So my laptop will send the packet to the gateway router, and then the router will figure out how to get it to the eventual destination, or at least to get it one step closer. Pass it on to another router. It gets a little bit closer, and then that other router will get a little closer, and they'll get a little closer, and they'll get a little closer until eventually it's there. Okay, so this is how we make the internet scale. My laptop does not know about all billion machines on the internet. It only knows about the hundreds or thousands in the Berkeley subnet. Well, it can find that out by ARP. It doesn't even know about that. And it doesn't know about all the other subnets. That's the router's job. And the router doesn't have to know about all billion machines on the internet. It only has to know about the thousands of subnets. Okay. And the lingo for this is autonomous system. Autonomous system is like a semi-local network that's associated with a single organization. Like there's an autonomous system for Berkeley. Autonomous system might consist of multiple local area networks and maybe multiple subnets even, but it's all under one administrator's control. So like there's an autonomous system for all the Berkeley IP addresses and another autonomous system for all the Stanford IP addresses. And within Berkeley, the Berkeley routers know about all the Berkeley IP machines, how to route from one Berkeley IP machine to another. Within Stanford, Stanford's routers know how to get from any Stanford IP address to any other Stanford IP address. Then Berkeley has a router that's a border gateway. It's a router that connects Berkeley to the rest of the internet. And if you need to send a packet to any other subnet that's not part of the Berkeley autonomous system, then it goes to that border gateway, that router, and that router figures out how to get it elsewhere. And those border gateways, those routers need to talk to each other to exchange information to figure out the graph structure. How do I, Berkeley needs to know who it's connected to. Berkeley's like, okay, I'm connected to Stanford and to, I don't know who we're connected to. Level 3 or something, I don't know. And then those organizations are connected to someone else, and eventually you can find a path that gets to Amazon. Okay, so the routers need a way to exchange information about that graph so that they know where to send packets. And there's a protocol for that called BGP, which takes care of routing. And routing is basically like, it's kind of like a Dijkstra shortest path computation on this graph, where each node is an autonomous system and each edge is a pair of like routers that are connected by some wire, like a fiber optic link or something like that. Except the tricky bit is that there is no one individual who has a global view of the entire internet. The routers have to cooperate to do something like Dijkstra's algorithm in parallel, distributed, concurrently, simultaneously. Yeah. Okay. Yeah. It kind of does, but it can be out of date because stuff can change. And so we need a way to like kind of keep them updated.
Central router to like.
Yeah.
Then that central administrator or the router gets to know, and then it updates all routers.
Right. Okay. Why not have a directory, central directory? I'm not an expert on that. I would suggest you take 168 and like ask the instructors there, why don't we all do that? I have a suspicion, but I don't know if it's right. My suspicion is that there would be a scalability problem with that. That one central directory would get overloaded. And also that it'd be a reliability issue. If that one central directory goes down or is not reachable, then the internet doesn't work. But I don't know. Maybe it could be workable. You'd have to ask someone who knows some networking more than I do. It's a good question. Yeah. All right. So let's say there's a sender that's sending an IP packet to the recipient, not on the same autonomous system. So they're going to need the help from routers to get the packet to the recipient. How do these routers know which way to send the packet? The sender might send the packet to autonomous system 1, and then the router for autonomous system 1 might know, okay, if I forward this to autonomous system 3, 3 can get there. And then 3 might know, okay, if I forward it to autonomous system 5, 5 can get there. And 5 might know, if I forward it to autonomous system 6, 6 will be able to get to the recipient, and then 6 will like forward it directly to the recipient. So they each might know, but how do they come to know that? Well, there's some, the BGP protocol just helps them come to know that. And the idea of this protocol, there's a lot of depth to it, but the simplified version of this is autonomous system 6, the router 6, has a direct connection to the recipient. Maybe the recipient is in that organization. So router 6 knows it can reach the recipient. So that's the starting point. Now it needs to tell the rest of the world, if you need to reach this recipient, here's how to do that. So what it does is it tells its neighbors. Router 6 tells its neighbors, says, hey, I know a way to get to the recipient. Actually, I got a really good way. It's direct, just one hop. Okay? So router 6 sends this to router 5 and 4. And now router 5 knows that it can get packets. It knows a way to get packets to the recipient. Just pass it on to autonomous system 6, pass it on to router 6, and 6 will get it there. So there's a path that starts with router 6, and then the recipient. And similarly for router 4 also now knows a way to get to the recipient. And then that's new knowledge for 5 and 4. So they got to help their neighbors. So 5 announces to its neighbors, hey, I know a way to get to the recipient. And it announces, 5 announces that to its neighbors. Who are the neighbors of 5? 3, 4, and 6. No need to send it to 6 because this path was already going through 6. So sends that to 3 and 4. Router 5 tells 3, I know a way to get to the recipient. Here's the path. And router 3 now knows a way to get to the recipient. Router 5 also sends to router 4, I know a way to get to the recipient. But router 4 ignores that because router 4 says, I know a better way. From router 4's perspective, going to 6 and then the recipient is better than 5 and then 6 and then the recipient. It'll be faster if it goes directly to 6. So each router keeps track of only the best way to get there. And this kind of propagates through the network by this kind of like, it's called the gossip protocol. You share with everyone. And by the time this is finished, everyone now knows a way to get to the recipient. And if anything changes, then there are update messages saying something changed. Like if router 6 can no longer reach the recipient, it might send an update to all its neighbors saying, oh, cancel that, I don't no longer know how to get to the recipient. And then maybe the recipient was now like moved and they took an international flight and then they land. And now they're connected to router 4. And so like first that update propagates through saying that, never mind, 6 doesn't know how to get there. None of us know how to get to the recipient. And then 4 starts sending out these announcements that it knows a way to get to the recipient, and all the paths get updated. So each router maintains a table of this. Well, not just for this one recipient, but for all possible recipients. That sounds horrible. Each router has to maintain a table with the path for every single IP address in existence. So BGP doesn't do that. It groups them by subnet. So it doesn't announce paths for individual machines. It announces a path for each subnet. So each router has a table with all the subnets in existence and the path that it knows of to get to that subnet. And whenever there's any changes, this kind of propagates through the network until everybody is updated and they all update their tables. Okay, so that's the BGP protocol. Yeah. Yeah. Yeah, since we're in security, that's the very next question is like, what are the security implications of this? And one, kind of like attack you can imagine in any protocols. What if someone lies? There's tens of thousands of routers out there. Maybe someone configures their router maliciously or someone hacks into a router. Can a router just lie? Absolutely. For instance, router 2 could just lie and claim that it has a direct one-hop connection to the recipient and start announcing that to its neighbors. And then router 1 will accept that and get fooled and think that the way to get to the recipient is by sending something to router 2, and then router 2 will get it there. And so if the sender starts sending packets after that lie, it won't make it to the recipient. It will go to autonomous system 2 and kind of stop there. If autonomous system 2 was malicious, why might it want to do that? What would be the motivation? Yeah?
It could go on one AS4, but now on because it can do whatever it wants, it could maybe like send it now to AS4, send it normally.
Yeah, router 2 can become on path for this communication and like eavesdrop on the communication, modify the communication, could censor the communication. If this is like a censorship thing, it could like eavesdrop on what data is being sent, and if it doesn't like it, block the traffic. In fact, router 2 becomes not just on path, but becomes a man in the middle, because the data now starts flowing through router 2. Yeah? Man in the middle, yeah. Man in the middle versus on path. Man in the middle would be the Wi-Fi access point in this room. When I'm sending messages to Amazon, they go through the access point and then get forwarded on to Amazon. So the access point can observe and modify those packets. On path would be anyone else in this room who has the Wi-Fi key, because you can decrypt the packet and observe what I'm sending, but you can't modify it. So on path is anyone else on the same, network that the packet is going through, so it can eavesdrop. Man in the middle is one of the routers, basically. Another reason that an attacker might do this is to pretend to be Amazon and receive all the traffic that people are sending to Amazon goes to router 2 now, goes to the attacker. So an attacker who controls a router can announce, I have a great route to Amazon, and all of a sudden people who are trying to go shopping on Amazon will be starting to send their packets to that attacker. So then they could maybe try to spoof the server and receive passwords people are sending to Amazon and so on. So BGP has no security. And this is the second of the threat that I was going to talk about. This is BGP hijacking. Any BGP router can just claim to have a route to some subnet or some website. And there have been incidents where this has happened. For instance, at one point about a decade ago, some ISP in Pakistan inadvertently misconfigured their BGP router to send out announcements that it had a great route to YouTube. And everybody who tried, and nobody in the world could access YouTube, because BGP got fooled by that into thinking that to go to the YouTube website, you should send the packets to Pakistan. And poor Pakistan, their link to the internet just got completely trashed, because everybody in the world who's trying to use YouTube was sending packets to them, and their network link got overwhelmed. So today there's some heuristics where system administrators will put some filters on the routes they'll accept from BGP to try to check for inadvertent mistakes like that, but that's not a very reliable security mechanism. So that's one problem with BGP. The other problem with this whole setup is that packets are routing is designed to be very simple. It's like fire and forget. If I'm a router, I don't worry too much about planning out the best way to get all the way to the end destination. I just need to know what's the next router in the path to send it to. And I don't need to know about where it came from. I don't need to know about what pre-routers it's been through before. I just look at a packet when it arrives, figure out where it's destined, and forward it on to one of the routers I'm connected to. You'll notice that routing process, it's very simple, so it can be done very fast. It doesn't involve looking at the source address of the packet at all. The source address is irrelevant for routing purposes. Routers don't look at the source address. The source address is only to help the recipient. So that brings to the other threat, which we've talked about before, is spoofing, IP spoofing. Anyone can send a packet and lie about the source address, put someone else's IP address in the source address. And that might get delivered all the way to the end destination, because routing works the same no matter what IP address is put in the source address. So you can potentially send a packet and put in the source address claiming that this is from Stanford, but it's not, it's actually from you. And then by the time it reaches the recipient will have no idea. We'll just assume it came from Stanford and send a reply back to the IP address that was supplied. Okay. Now, this doesn't always work because we know that IP spoofing is a problem. So responsible ISPs actually have put in place some extra filtering where they do check the source address and they check like, does this source address look like, let's see, if the packet is coming from one of their customers, they check the source address to check, does this source address for one of the subnets that I've assigned to my customers? If not, then something bad is happening and drop the packet. But not all ISPs do that checking because it's some extra cost and some extra administrative hassle and configuration to keep track of. And so if you try to send a spoofed IP packet, it might make it through if you're going through the less responsible ISPs, or it might get blocked if you're going through a more responsible ISP. Okay, so bottom line is basically no security at the IP level. You could spoof, you can pretend to be a server, you can pretend to be a client, you can become a man in the middle. There's very little security protections at the IP level. So if we need some security, it's going to have to come from higher levels. So let me start telling you about the next higher level. On top of IP, we use TCP, which is a protocol designed to provide some features that IP doesn't have. IP is designed to be very simple, have very few features so that it can be routed very fast. But the downside is there's stuff we want that it doesn't provide. IP is unreliable, but we would like our network connections to be reliable. IP is unreliable because that enables us to build routers that are like faster and can handle more traffic. But it means that the end hosts have to come up with some other way to provide reliability. Also, IP, not just packets can get lost, but also they can get reordered or delayed. They can get corrupted and like errors can be introduced. TCP, we probably don't want that to happen to our data. So TCP was introduced to deal with all of this. So I suggest we figure out together how you might design a protocol like TCP to solve some of these shortcomings of IP. The first shortcoming is that IP packets are limited in size. They can only be a maximum of 1,500 bytes would be a typical length. Can't send any packet longer than 1,500 bytes of data. But like I may want to download files that are larger than 1,500 bytes. So what do we do? Yeah? Break it up into multiple packets. Okay, great. Great. Absolutely. The sender should break these up into multiple packets, all of them small enough. Love it. Break it up into packets. Any issues we're going to have to take care of when we do this? Consider padding. You don't, because IP packets can be any length. So you don't need to add some padding. But good thought. Yeah. Any other issues we got to take care of when we break them up into multiple packets? Yeah? Order. What were you going to say? Packets could be corrupted or there could be noise. So we're going to need a way to deal with that if a packet gets corrupted. And I guess there's two aspects to that. You're pointing out that if one packet is corrupted, we don't want that to mess up all the other packets. That would really suck. And also, we're going to need a way to recover for that one packet that was corrupted. Okay, so good. So we got some issues. We got order, we got to deal with order, and we got to deal with like packet loss or packet corruption. Maybe we can start with order. How could you, I said before that packets could get delayed or reordered. So I might send packet 1, 2, 3 in that order at the sending side. But it might turn out that they get received in the order 231. It can happen. So what could we do about that? Could we put an index? Absolutely. Yeah. Mark, this is packet number 1. This is packet number 2. This is packet number 3. Absolutely.
So you would have to wait for both the packets to arrive to decode or decrypt it.
Good. Okay. So the sender's job is pretty easy. Just mark each packet with this this counter, right? This index. Split up the message. What do we do when we're receiving them? When receiving them, the receiver takes, packet 1, packet 2, packet 3, and then recombines them together. What should the receiver do if they're arriving out of order? Like the receiver receives a packet marked packet number 2. Wait for all of them. Store a copy of that and wait. Yeah. So the receiver has to store a copy of 2, and then let's say 3 arrives, store a copy of 3, can't do anything with that yet. And then when 1 arrives, good, we got them all. Now we can combine them. The receiver can combine them and give them to the application. Okay. So we just discussed about how to handle out of order. It turns out that TCP uses a slightly different solution than yours, but it's conceptually very similar. We were talking about numbering each packet, which is a very natural thing to do. 1, 2, 3, 4. It turns out what TCP does is it doesn't number the packets, it numbers the bytes in the data stream. So at the moment, I can't give you a really good motivation for why, but hopefully it makes sense that that would also work. Okay. Yeah.
Because I received 3, 1, and 2. I don't know.
Yeah. It seems like I should send 1 of 3, 2 of 3, 3 of 3. Got to wait for all 3 to arrive before they can be delivered to the whatever the receiving application is. Yeah. TCP actually has a little tweak for that. TCP doesn't mark 1 of 3, 2 of 3, 3 of 3. When TCP reassembles, it doesn't guarantee to give you back, it might give you the first part of the message, it might give the recipient, it might deliver the first part of the message first, and then later deliver the second part of the message. So TCP is not, the abstraction that TCP provides is not the sender sends a long message, the recipient receives that long message. Rather, it's the sender sends a stream of bytes, the recipient receives a stream of bytes sometime later. So if the recipient receives 1 of 3, but doesn't have 2 of 3 or 3 of 3 yet, it can actually deliver that 1 of 3 to the application that's expecting this traffic. And then when if it next receives 3 of 3, can't deliver that yet, then when it gets 2 of 3, then it can deliver 2 of 3 and 3 of 3 to the software application. So in that way, that TCP avoids having to mark it as 1 of 3. It just marks it as 1, 2, 3. And we don't have a separate counter for each message. We just have a incrementing, it just keeps incrementing. When you have a new message to send, it can be broken up and the counter keeps incrementing from there. You don't reset back to 0. But those are details. Your design was perfectly fine, too. It's just there's multiple ways you could do it. Last problem is the problem you mentioned, that packets could be corrupted or dropped. They can get lost along the way. Like if a router gets too busy and receives a packet and it's overwhelmed, it does like what I do with my email. It's like, oops, delete. It just declares bankruptcy and deletes all the packets that people have sent to it to give itself a chance to get caught up. It's kind of crazy. So packets can get lost along the way. Also, they can get corrupted. There can be noise. There could be, you know, some errors that occur during transmission. And then when it's received, probably the checksum will be invalid. And so the recipient will be like, ah, that was errors in this packet. I can't use it. I have to throw it away. So it's a lot like a packet getting dropped. Okay, so packets can get lost, dropped or corrupted. What can we do about that? I don't like that. As a sender, I want to make sure my data gets there. I want a reliable service. So how could we make it reliable? Yeah? Yeah, forward error correction, error correcting codes. A really dumb version of that is send the packet 5 times. Hopefully one of the 5 will get through. Error correcting codes are like a more efficient version of that. It's got some issues. One issue is, even if I send it 5 times, there's no guarantee that all 5 of them get through. Maybe a router got overwhelmed for the next second, and all 5 of those got lost, got dropped. But then the router kind of comes back to its senses. I would like my networking protocol to like automatically figure that out and make sure the data gets through. So error correcting codes are a more efficient version of that, but they have the same problem. So they're not really fully satisfactory solution. We still need a way to deal with the fact that all of the data might get lost. Does that make sense? Yeah, no, it's a great idea though. I really love it. It's one of the major ways of dealing with errors and loss in packets. It's just that I think we want something more for internet connections. So another technique is an acknowledgement. The recipient acknowledges receipt. And as a sender, if I send it and I get back an acknowledgement, then I know it made its way through. Yeah. How would the recipient know whether to send the acknowledgement because maybe it hasn't got the full message yet? Yeah, what could we do about that? That's a puzzle, isn't it? There's no cryptography in TCP. You don't need any crypto to do this. Yeah. Asymmetric vibes, yeah. Yeah, what do you think?
Bytes number, you notice that numbers missing in the middle, and that would be part of it.
I like it. If things are numbered, then the recipient, when they send the acknowledgement, their acknowledgement can indicate what they've received. And a way to indicate what you've received is to provide the indexes of the packets you received or the sequence numbers for the bytes range that you received. Does that make sense? So the recipient sends back an acknowledgement when it gets the data that indicates what message, what packets, or what bytes it's received. Yeah, absolutely. Guess here we go. Now that you get to some of the trickiness of networking, is that the sender sends the data, it might get lost, and there's no acknowledgement comes back in that case. Or the sender might send the data, it might make it to the recipient sends an acknowledgement, but the acknowledgement might get lost. No acknowledgement received. From the sender's perspective, those two scenarios are indistinguishable. What do I do? I can't tell. As a sender, if I don't get an acknowledgement, I can't tell whether my message got lost or whether the acknowledgement got lost. Send it again either way. I got to do the same thing either way. If I don't get an acknowledgement, I got to send it again. Seems like the only possible strategy. Send it again. If I don't get an acknowledgement, send it again. So there's some timeout. If I don't get an acknowledgement within 10 seconds, send it again. Okay? But wait, what do we do now? What if the first copy was received, the acknowledgement got dropped, and I sent it again, so now the recipient is getting another copy? Yeah? The receiver will send another acknowledgement. And then what do? I sent it, I meant to send it only once, but the receivers got copies? Do you see the potential for a problem here? I sent my bank. Please transfer please pay $1,000 to the bike shop. But I don't get back an acknowledgement. So I send it again. Please pay $1,000 to the bike shop. Depending on whether my message got lost or the first time, or the acknowledgement got lost the first time, maybe my bank is sending $1,000 or $2,000 to the bike shop. Uh-oh. And I can't tell, because either way, I didn't get an acknowledgement the first time, I did get an acknowledgement the second time. Do you feel the pain? I feel like I have to first help you feel the headache before I can give you the aspirin or the Tylenol. You feel the pain. Contact the bike shop and be like, don't cash the second check. I'm not happy with that. As a sender, there's nothing, I can't solve this. I'm going to need the help from the recipient. So how could the recipient help? Yeah? Oh, can the recipient detect that this is a duplicate message? Can the recipient tell that it's getting two copies of what was intended to be the same thing? What do you, oh, wow. I feel like so philosophical here. What do you mean by the same message? Doesn't that sound deep? But it's actually not that deep, but it sounds deep.
The second message, and they see the same message, then they're at the same message.
Same bytes?
Same bytes.
That's got a problem. I like it. I like where you're going. Okay, so you detected duplicates. Idea is if we see the second one has the same bytes as the first one, then the recipient will say this is a duplicate. And if the recipient detects a duplicate, what should the recipient do?
Wait, what if they make the transaction after getting it the first time, and then, oh wait, then they're not gonna do the transaction after the second time.
You just threw away your good idea. I heard you say only do it once. So help me out. What should the recipient do if they detected that they've got a duplicate? Yeah? Ignore the duplicate. Absolutely. I already got that. Thanks very much. Because send an acknowledgement. I see you resending this. I'm gonna send an acknowledgement again, but ignore it the second time. All right, we got the basis of a solution. Sounds good. I see some hands. Is there a timeout window? The sender has a timeout window. The sender will send a packet and expect an acknowledgement within a certain timeout. And if it doesn't get acknowledgement within that timeout, it'll send another one.
What about here? With that second, that's it.
So there's no encryption at this point. I'm teaching about how IP and TCP work, and they're not encrypted. They're not doing any cryptography. So it'll be exactly the same bytes. Yeah, what if it was intended that someone wanted to pay 2 times? They actually sent 2 messages. Then the recipient is going to wrongly ignore the second one. I'm not happy with that. Yeah, so there's a problem with the scheme we've got, which you've correctly diagnosed. So we need to tweak. We're on a good path, but we need to tweak the scheme we've got. Did you have your up? Did you want to try?
Need to put some kind of boolean in there, which indicates that this is a duplicate of the message already sent.
Oh, the sender could put a Boolean with this if it's a duplicate? Oh, interesting. I haven't thought about that. I'm a little worried I'm a little worried about the fact that telling the difference between the first two get dropped and the third is received versus the first is dropped and the second is received. So maybe a Boolean is not enough. Maybe we need a counter. And now I'm like, oh, another counter? Yeah?
Not work, because you can have, I send the first message, and I have to resend it once, right? So the resend counts two. And then they send another message with the exact same content, but like I've actually sent a different request. Like my first request went through, I'm now sending a second request with the same content, and it fails twice, let's say. So that resend counter is like 2. And that's counted as duplicate of the first. So what we probably would want is more of a packet ID to uniquely identify every like send that we want to do. Like every like different send.
Yeah, this is so tricky, isn't it? Because we want to distinguish between TCP resent a packet that was dropped versus the sender wanted to send this, a message and then send the same message a second time. We have to find a way to distinguish between that. So we really want a packet ID that we can use to identify so that the resend is going to use the same ID, right? But if it's a new, if the sender wants to send the same data a second time, now it's a new ID, right? Yeah, so that's what we really want, is we want this ID. So we could have an ID. It turns out we don't need an ID. We already got an ID. The sequence number is our ID. The sequence number counts, it's like the idea of an index for each packet, except we're not counting packets, we're counting bytes in the byte stream. But it could be just as well be an index. We can use that as our ID. So if a packet gets dropped, we resend it and we reuse the same ID. We reuse the same sequence number or the same index when we resend it. And then the acknowledgement includes the ID of what was received. So it turns out that eliminates all the ambiguity. It's like a very simple solution. It's kind of beautiful. And if you try to design it on your own, it's like quite tricky to figure out how to solve this. Yeah, work with what you have. Yeah. Yeah, sequence numbers are 32 bits. They can roll over. Usually it'll probably take here's a heuristic engineering argument that's a little bit unsatisfying. It's probably take long enough that it's unlikely that any old packet will be still around within that time period. That was the design basis. I don't know, there could be some weakness there. Originally the internet, when the TCP was designed, the internet was a lot slower. So it would have taken a really long time to send 2 to the 32 bytes. Now we can send 2 to the 32 bytes pretty fast, actually. Certainly minutes, maybe some people with really good connections might be able to get in seconds. Yeah, so there's a little bit of a engineering heuristic there. Maybe we should have had a 64-bit number sequence number, but we didn't. Yep.
On failure mode, like, if we've been trying this out for 30 seconds and nothing has been happening, like nothing has been working, probably drop it. If, like, for example, internet shut down, or we live in Hawaii and there's only one like wire that connects us to the rest of the world.
Yep. Yep. So there are a bunch of details here that I haven't told you about. There is a way that TCP selects the timeout for when to resend. And I forget, but I think it's based on past. It keeps track of every time it sends a packet and gets back an acknowledgement, how long did that take? And so it can maintain an estimate of how long it should expect for acknowledgements, and then has set some timeout. And then if you don't get an answer, then you like double the timeout or something. I don't know. I don't remember. And then there's some limit if it, it's like more than 30 seconds and you just give up, or I don't know I don't know the exact details, something like that. So you have to talk to a networking person to get the right answer there. What's that? We should have Aaron come in and tell us all these details. Okay, so that's TCP. Congratulations. You invented several of the main ideas in TCP. It's a way to send a stream of bytes. So from the sender's perspective, the sender is sending a sequence of bytes, maybe with some pauses in between. The recipient will receive the same sequence of bytes, but just delayed, and maybe in different groupings. TCP ensures that the ordering is preserved. So if packets get reordered, TCP will like bring it back to the correct order. TCP ensures reliability, make sure that the data will get there. Keeps trying until it does. And TCP also enables you to run multiple software applications on the same machine. You've only got one IP address for your machine, so those software applications are identified by port numbers. Each software application gets its own port number. And each port number corresponds to its own TCP connection and its own like byte stream, so the applications don't interfere with each other. So from the perspective of writing a software application, I make a TCP connection, and it's as though I had a network link that was perfectly reliable and that's not affected by anyone else's connections. Yes. Okay, good. We haven't talked about attacks, so let's talk about attacks. On-path attackers are hard to think about. I suggest we start with off-path or man in the middle. Which do you like? You like man in the middle. What can a man in the middle do if I've opened a TCP connection with some server and there's a man in the middle, one of the routers that this data is going through is malicious. What could the man in the middle do? Modify bytes in this TCP connection. What else? Yeah?
Some way, like, sending a fake acknowledgement, or like whether he sends fake acknowledgements, sends fake packets, or like any of the what it usually just ends up being is like, oh, there's just one packet that like never comes, or like TLS.
Okay, so one thing a man in the middle can certainly do is just like block the connection, like terminate the connection. An example that would be the Great Firewall of China, which is like doing censorship. If you connect to some websites they don't like and send some data they don't like, they might just like end the connection. So a man in the middle could certainly end the connection early, block any further data. I think I'm hearing some debate between the two of you about whether a man in the middle could modify data. Am I hearing some debate? If I'm making an unencrypted connection to my bank and there's a man in the middle, the man in the middle might want to, instead of change that from saying send $1,000 to the bike shop, to say send $10,000 to, the attacker. Absolutely. I just am trying to figure out what's possible. Yeah. Okay. Okay. Well, I want to know from the application's perspective what a man in the middle could do, even if whether you consider that an attack on TCP or not. So let's include everything. So, okay, I think we're in agreement that a man in the middle could modify the data that's being sent over the TCP connection, could block the TCP connection. What else? Confidentiality, integrity, availability. Block is defeating availability. Modify is defeating integrity. What about confidentiality? Could a man in the middle learn what data is being sent over the connection? Yeah, so eavesdrop. So a man in the middle could eavesdrop, modify, and block the connection, all three of those. How about an off-path attacker? Can an off-path attacker eavesdrop? No. The data doesn't go anywhere near them. This data is going from California to Oregon to, Seattle to Amazon. Someone in Bulgaria, they have no chance to see the data. Off-path attacker cannot eavesdrop. Can they modify the data? No. Can they block the connection? It turns out no would be a reasonable answer, but maybe yes. But we'll come back to that. Yeah. Yeah, right. We got to think about what if the off-path attacker sends some like bogus data or bogus acknowledgement or something. Let me come back to that one. You wanted to know about an on-path attacker. That is the trickiest one of all. Can an on-path attacker eavesdrop on the data sent over the connection? Yeah, because the data is going through a network that the attacker is on, and if that's a shared network, then they can eavesdrop on it. Can an on-path attacker modify data through the TCP connection? No. Except we're going to see it's actually yes. But no is a good answer. It should be no. The answer should be no. It just turns out to be yes. Okay. So I'm going to come back to on-path attackers. Before I do, I see a question on Zoom from, a long time ago saying, how do they know that? Hey, y'all on Zoom. Did I happen to answer your question? If not, catch me up here. No, I didn't answer it. Okay, help me out. You can either unmute or type in the chat. I want to help you. How does a router know that? Okay, help me out a little more. You forgot the question. Oh, sorry. Oh, it was like 40 minutes ago. I didn't answer your question, and it's long since disappeared. Thank you. Okay, sorry about that. Okay, I'll try to keep an eye on the chat better. My apologies. I screwed that up. Okay, so yeah, I love it. You're asking about what the security implications of TCP are. Thank you. That's what I want to talk about. But I guess I'll mention a little bit like port numbers. I don't need to talk about port numbers. You know about port numbers. Basically, ports help distinguish between multiple applications. And each application is going to get its own port number. And so when packets arrive at a machine, when TCP packets arrive at a machine, the port number tells the software which application this should be delivered to. Is it the web browser? Is it the Spotify app? Is it something else? So a TCP packet, remember this layering diagram, right? So TCP is on top of IP. So that means that a TCP packet starts with an IP header because it's sent through on top of IP. And then there's a TCP header, and then there's the data. So the IP header will have the source and destination IP addresses, and the TCP header will have source and destination port numbers that identify applications on those machines. I want to talk a little bit about sequence numbers. I gave you the high-level view of TCP, but I left out some details that actually matter. So I'm going to talk to you about these details right now. I said that we identify data by these sequence numbers. Instead of a message index, we actually have a counter for the bytes in this byte stream. That's what the sequence numbers are. And there's two spaces of this, or two sequence numbers to keep track of. One is for data from the client to the server, and one is for data from the server to the client. And there needs to be some initial sequence number for the first byte of data that's sent. And the obvious number would be like 1. 0, because we're computer scientists. Thank you. Absolutely. Right on. I accept your correction. Except TCP doesn't do the obvious thing. It starts from a random number and counts up and then wraps around. And we'll talk about why in a moment. It's basically security reasons. but 0 would be a natural starting point. Okay, so if the client is sending a message with the bytes hello server, then you can think of each byte as receiving a sequence number, being numbered by a sequence number. So the H might be number 50, and then the E would be number 51, and so on. So each byte in this stream implicitly has a sequence number. I'm not saying that they're sent in the packet. That would be crazy. You wouldn't send both the bytes and all those numbers. It'd be enough to send the bytes and the number 50. And then the receiver could figure out the numbers for all the other bytes, right? No reason to waste space. But implicitly, every byte has a sequence number. And then if the server sends data to the client, those bytes will also have sequence numbers, but it's a totally independent sequence number. It's an independent space of sequence numbers. It starts with a different number than the other direction. So in this case, starting with 25. And TCP, to establish a TCP connection, there's some setup that has to happen. And one of the things that needs to be done in that setup is both sides have to agree on these initial sequence numbers that they're going to use for the first byte in the connection. So conceptually, the way that happens is like, oh, I broke my animation. Okay. Sorry. Okay, I messed up my slide. But conceptually, you could imagine the way this could happen, a very reasonable design, would be the client says, I've selected a sequence number for data from client to server. So the client selects the initial sequence number for the data the client is sending. And then the server needs to know that. So the client sends a message to the server saying, hey, the initial sequence number that I'm going to use is X. So now you know. And there's a name for that packet in TCP. It's called a synchronized packet, or SYN for short. So they can synchronize on the initial sequence number. And we always want to acknowledge everything. You got to acknowledge everything because there could be packet loss. So the server will send back an acknowledgement and say, I got your message, got it. Okay, we'll use X as our initial sequence number. And conceptually, what you can imagine the server do is sends back something saying, I acknowledge X is the initial sequence number you're going to use. For whatever reason, it sends back X plus 1. I don't really know why, but it does. So there. And then we need a sequence numbers for data that the server sends. So the server picks that initial sequence number. I'm going to call it Y. It's just a number, a 32-bit number. And the server will send that to the client so the client knows. Again, in a synchronized packet, a SYN packet. When the client receives that, we got to acknowledge everything, right? So it sends back an acknowledgement to the server saying, got it. The initial sequence number you're going to use is Y. I understand. I'm ready for you. Okay? And just as before, for some unknown arcane reason, doesn't actually send back Y, it sends back Y plus 1. I don't know why. I don't think there's any good reason. And then once this has been done, both sides know the initial sequence numbers for both directions of the connection. They're now like synchronized and the connection is established and they can now send data. All the setup is finished. And so they can send data using these sequence numbers. Okay? So that's conceptually the idea of how this setup works. Anytime you start a new TCP connection, you do this setup. Question?
Let's say you say like, so you send like three packets, like 1, 2, and 3, and then they only receive like 1, so then they send 2, so you will only send
I'm lost. Can anyone help me?
like, so like the like X plus 1 is like, so you know, like we're good up till X.
Ah.
Up till
Oh, yes. Yes, you're absolutely right. Thank you for asking. Yes. That is conceptually what these acknowledgements mean. When someone sends an acknowledgement with the sequence number X plus 1, that you should interpret that as meaning I'm expecting the next byte that I'm waiting for is x plus 1. I've got everything up to and including x. And I'm expecting the next one will be x plus 1. So yes, you're right. Why did they make that choice? I don't know. They could have done it differently, but this is just an arbitrary choice. But it turns out that's not actually how the three-way handshake in TCP works. There's a little bit of an optimization. You'll notice that the setup requires 4 packets, SYN, then ACK, SYN, then ACK. Why did I call it a three-way handshake if there's 4 packets? It's because there's not actually 4 packets in the real TCP. The real TCP has a little trick to reduce the number of packets that need to be sent, to send only 3 packets instead of 4 packets. Can any of you see how you might be able to reduce the number of packets without making any like very fundamental changes? Is there any simple trick? Yeah. Merge those 2 green packets in the middle, the ACK followed by the SYN. They're right after each other. Just send them in 1 packet. It's exactly what TCP does. So there's a little optimization in there. So the way it actually works is the client picks an initial sequence number for the data it's going to send, sends that to the server in a SYN packet. The server acknowledges that, but also at the same time, this is the coalescing part, also has picked an initial sequence number for the data the server is going to send and sends that in the same packet. So this is a packet that now is for both SYN and the ACK, so we call it a SYN-ACK packet. It has both a sequence number, which contains the initial sequence number the server is going to use, and an ACK, which is an acknowledgement of the sequence number that the client sent. And then the client sends an ACK packet to acknowledge receiving the server's SYN, and then the connection is established and they can send data. They both have sequence numbers they can use to label the data. And so if now the server was sending some data to the client, the sequence number it would use for the first byte of data it sends is, you tell me, y plus 1 or x plus 1? Server to client, y plus 1, that's right. Server picks the initial sequence number for the data it's going to send, so y plus 1.
Sequence X,
In TCP, every packet has a sequence number that indicates the sequence number of like the first byte of data. This ACK packet is a crazy packet that has no data, has 0 bytes of data, but we still include the sequence number. Of the packet, yeah. Okay, so TCP software on each side keeps track of all the connections that are open. For any open connection, it keeps track of which of these like packets, messages have been received. A connection is uniquely identified by the source IP address, the destination IP address, the source port number, and the destination port number. And we're using TCP. So you might hear someone talk about a 5-tuple. That's these 5 values, and they uniquely identify a TCP connection. Yeah, we already said if the recipient receives partial data, as long as it's contiguous, it can be delivered immediately to the application. If there's a gap, then it has to wait until the gap has been filled. So now, remember I said the natural thing would be that you start with sequence number 0, or maybe 1, if you let me get away with it. But TCP doesn't actually do that. It starts at a random sequence number. So if the initial sequence number was X, then the ith byte receives the sequence number X plus I. So the first byte will be X plus 1. Second byte will be X plus 2. Third byte will be X plus 3 instead of 1, 2, 3.
the diagram
Huh? That was a little bit of a weird thing because that packet had no data in it. So it's like x plus 1 is like the sequence number of the first byte of data in this packet if it were to have data, but it doesn't. But I still include the sequence number anyway. Well, it depends how you're counting I. The first byte would be x plus 1, have sequence number x plus 1. Yeah, x plus I plus 1 if you're 0 indexing. X plus I if you're 1 indexing. Okay, so a packet sequence number is the sequence number of the first byte of data. Remember I said you don't have to send all the sequence numbers of all the bytes of data, just the first byte. So that's part of TCP header. And then another part of the TCP header is every packet has an acknowledgement field. Always included. That indicates basically what has been received. What's the longest contiguous prefix that has been received so far? What's the next byte that we're waiting for? So the ACK field is a sequence number for the next byte the first byte that we haven't received. The first byte that is like, should come next that we haven't gotten yet. Or you could think of it as the last byte that we've successfully received plus 1. Yeah, we desperately need a break, don't we? How about we take a break right now? Good. Let's have a break. 4-minute break.
Class is 161, maximum.
All right, so the way this looks is if the connection is established and there's some data to be sent, the first packet, like if the client is the first one sending some data, the first packet will contain the initial sequence number that the client chose, will acknowledge the initial sequence number that the server chose, and then have some data. And let's suppose that has length A, like 100 bytes. Then the acknowledgement from the server will acknowledge receiving all 100 of those bytes by including in the ACK field the sequence number of the last byte of the data plus 1. So in other words, the server will send back an ACK that is a sequence number of the next sequence number for the next byte it's expecting from the client that it hasn't gotten yet. So in this case, that would be x plus 1 plus A. And we always do this coalescing business. So the server is sending some data. If the server has some data to send, it includes the data it has to send in that same packet. So you can think of the packet from the server as like a data packet with sequence number y plus 1 and length b. But it's also an ACK packet acknowledging receipt up to but not including sequence number x plus 1 plus a. And then when the client receives this data, it sends an acknowledgement. And if it has any data to send, it includes that in the acknowledgement. Might wait a tiny bit before sending the acknowledgement just in case some data appears. Why is the length sent? The length is included in the packet header so that the recipient knows when to like stop listening to the radio. It's only one. Yeah, this length is in bytes. The number of bytes of data in that one packet. So you could have a packet that contains only 1 byte of data, or it could have 100 bytes of data, or it could have 1,000 bytes of data. All right, so that's how TCP works. If a packet is dropped, then the recipient doesn't receive it, so the recipient doesn't send an ACK, so the sender resends it. If the packet is received but the ACK is dropped, sender doesn't get the ACK, sender resends it. And then the recipient can tell this is a duplicate data because it's using the same sequence number for data it has already received. So when the recipient receives a packet with a sequence number for data it's already received, it ignores it. That was a duplicate. And by the way, TCP has some sophisticated, very clever, very cool control theory mechanisms to keep track of how busy the network is and figure out how fast it can send data and throttle itself back if the network is like overwhelmed and if the network has free capacity to like send as fast as it can. And the way it uses that, it uses these packet drops as the feedback. So if it gets a packet drop, it assumes the network is busy and it starts sending at a slower rate. And if it's been sending for a while and doesn't have any packet drop, then it figures, oh, maybe there's even more capacity. Let's try sending at a faster rate and see if that works. So it's constantly adjusting based on the amount of data you have to send and the capacity in the network. To end a connection, there's a special packets for that. The fin means, okay, I'm done, orderly shutdown of the connection. And a reset packet means, whoa, something went really wrong. Shut the whole thing down now. Okay, so the TCP header has a bit vector in there. You can, with 4 flags that can be turned on or off for each packet. It could be the ACK flag can be turned on or off, the SYN flag can be turned on or off, the FIN, and the reset. So for instance, SYN ACK packet is one that has the SYN bit set and the ACK bit set in this field. You don't need to know this, but here's what the TCP packet structure looks like. There's the port numbers, sequence number, the acknowledgement number, and then some stuff you don't need to know. a checksum on the data, and then the data. Checksum it's like a hash function. It's a way of detecting if there were any errors in the data. If there are errors in the data, probably the checksum will be not match, and so the recipient can detect, I shouldn't use this data, there were probably some error in it. It doesn't provide a way to correct the error, just to detect the error. It's not cryptographic. There's no cryptographic keys. So if there's a man in the middle, the man in the middle could change the data and then modify the checksum to match. So it's not a security mechanism. It's a way of dealing with errors, random errors. It's not integrity. It's like a reliability kind of thing. Okay, so one threat with TCP is TCP hijacking. If there's an existing TCP connection, an attacker might want to modify the data in that connection or inject new data. And we already said that this is easy for a man in the middle to do. Turns out it's also not hard for an on-path attacker to do. To inject new data into the connection, the attacker sends a TCP packet with the right sequence number. Has to have the right sequence number for the recipient to accept it. If the sequence number is way off, then the recipient's going to be like, well, there was a huge gap. I better store that, but I'm not doing anything with it right now. So the attacker needs to know what sequence number to put in the packet. This is where those initial sequence numbers come in. If we started sequence numbers from 0, it might be easy for an attacker to guess what sequence number to use. But because TCP starts from a random initial sequence number, it's hard for an attacker to guess what sequence number to know, unless the attacker can somehow figure it out. A man in the middle can easily figure it out because a man in the middle can eavesdrop and observe what sequence numbers are being used. What about an on-path attacker? They can eavesdrop too. So they can observe the sequence numbers. So they can create spoofed packets and put in the correct sequence numbers in there and send a spoofed packet to the recipient. And the recipient will think that the sender sent that, but it was actually the attacker sending it. So an on-path attacker can inject data into a connection. They're sending something, the sender is sending something with the same sequence number. Whichever one gets there first will be accepted by the recipient. Whichever gets there second will be ignored as a duplicate. So it's like a race condition. But if the attacker's faster than the sender, they can inject data into the connection or modify data in the connection. Yeah, what's the use of the random sequence number if an on-path attacker can just observe it? Why bother? Does anyone? Doesn't help against a man-in-the-middle attacker. Doesn't help against an on-path attacker. You probably guessed where I'm going with this. What's the third type of attacker? An off-path attacker. Can an off-path attacker do this? An off-path attacker cannot eavesdrop. So they can't learn the sequence numbers. So an off-path attacker cannot mount this attack. So the initial sequence number helps protect against off-path attackers. That's why we have a random initial sequence number. The off-path attacker won't be able to guess what sequence number to use, and so if they try to do a data injection attack, it'll fail. Probably. I mean, they might get lucky. There's some chance that the attacker could correctly guess a good sequence number. Like at least a 1 in 2 to the 32 chance that an off-path attacker could just blindly guess what sequence number to put in. So if they made enough tries, they could probably be successful, but it'd be very expensive. It involves sending a lot of packets for the off-path attacker. And so we mostly discount that threat as not realistic, not something we need to worry too much about. So TCP is this funky protocol that has security against off-path attackers, but is not secure against man-in-the-middle and on-path attackers. That's something. That's actually something significant from a networking point of view. It means that my attack surface, the people who can attack me, is limited to the on-path and man-in-the-middle attackers. If I have a connection to Amazon and it goes through 10 routers, those 10 routers could attack me. Maybe other machines on the same subnets could attack me. But random machines on the internet is unlikely to be on path. Most machines are going to be off path. Maybe, hundreds or thousands of machines might be on path, and I'm vulnerable to them. But all the rest of billions of machines are off path, and I'm safe from them. So it's actually, in some sense, pretty good. From a cryptography perspective, we would say it's terrible because there are those, 1,000 people who we're vulnerable to. But from like a pragmatic, this is a difference between the cryptography perspective and the network security perspective. The cryptographer says, I demand the strongest security level possible because I can achieve it. And the network security expert says, it's good enough. It's not perfect, but whatever. I'm calling it a day and going home. Okay, the other threat with TCP.
Hi, Professor. Your microphone died.
All right, Zoom folks, can you hear me now?
Yes, we can.
Yes.
Thank you.
All right, thank you for helping me out with that. All right, just interrupt if you can't hear me. Hopefully this is going to work. I know it's not as good, but we're flexing with tech issues today. All right, so that's reset injection. And the idea is with data injection that if the client is sending some data and then the server is about to send a response, an attacker can send fake response. The attacker can do that by sending a spoofed packet, the source address being spoofed to the server. It's not actually from the server, it's from the attacker, but the attacker spoofs the source address. And then to make sure that the spoofed data, this evil data, is accepted, the attacker needs to know the correct sequence number to fill in. If the attacker does know the sequence number, then they can inject this data into the connection. As long as the attacker's packet gets there before the server's legitimate packet, then the attacker's packet will be accepted and the server's packet will be ignored. Okay. Another threat with TCP is TCP spoofing, that if I'm malicious, I can try to create a TCP connection to log into the Hive machines, pretending to come from your machine. Now, it won't work because I don't know your password, but it used to be that they were set up so if it came from the right IP address, you were just let in with no password. And that was totally insecure because of TCP spoofing. So in TCP spoofing, I would try to open a TCP connection with that Hive machine, but spoofing my source address to be your machine's source address. If you try to do that, it doesn't work. It doesn't work because I send the SYN packet with a spoofed source address to the Hive machine. The Hive machine responds with an ACK packet, which goes back to the source address, goes back to your machine, and I can't see it. If I'm off path for that, I can't see the response. So I don't know the right sequence number, so I can't follow up with the ACK for that. to finish the three-way handshake because I don't know what sequence number to fill in. So naively, spoofing a TCP connection is not possible for off-path attackers, but it is possible for on-path attackers, as long as the initial sequence numbers are random. I said they're random. That was a little bit of a lie. Initially, they were based on a timestamp, so they were actually guessable. So it's actually possible to do TCP spoofing. If I'm malicious, I send the SYN packet, the ACK packet goes back to your machine, then I send an ACK packet with my guess at the correct sequence number that the server has chose. Acknowledge with an ACK for my guess at what sequence number the server has chosen. And if that's based on the time, then I might be able to guess it correctly. And so I might be able to finish the three-way connection. And then I might be able to send some data to the server using the right sequence number. So the fix for that was, instead of using a timestamp, use a true random 32-bit value. And now TCP spoofing requires the attacker to guess the 32-bit initial sequence number. So the attacker has a 1 in 2 to the 32 chance of success, which is pretty low. It's not 0, but it's low enough that it's hard to do. Okay, so yet another example where TCP, modern TCP, is secure against off-path attackers. Off-path attackers cannot do TCP spoofing, but it's vulnerable to man-in-the-middle and on-path attackers who can do this spoofing a connection. Question?
After they send data with a different link, that would kind of mess up the acknowledgement.
Oh, you are really paying attention. Yes, you are so right. I glossed right over a detail of this injection. If the attacker sends data of a different length, everything's going to get desynchronized and like, oh my gosh, stuff's going to happen like crazy. Yes, you're right. You're right. So you could think of this as the attacker is limited. They get to send one packet and then stuff's going to go haywire. I think I read a paper once that said how the attacker can kind of keep going. If you like analyze exactly what's going to happen in that situation, then there's a way the attacker can keep injecting more stuff if they want. And it got complicated and messy, and I understood it 20 years ago, and I don't understand it anymore, so I can't explain it to you today. So I think it's actually possible to make up for those problems. But it turns out it doesn't really matter in practice, because in practice, often one packet is enough to do all the harm that the attacker wants. You are so paying attention. I love it. Yes. Okay. So spoofing and spoofing attack. The SYN packet is sent by an attacker with a spoofed source address. The server's reply will go back to the source address that this is claiming to come from, not back to the attacker. So the attacker can't see it if they're off path. Then the attacker spoofs an ACK packet, filling in the guess at the sequence number that the server chose, the value Y. And if the guess is right, then the server accepts this is a fully set up connection and will accept whatever evil data is sent and will treat it as a connection coming from that spoofed IP address. Today, hard to do unless you're on path because it's hard to guess the initial sequence. Okay, so basically TCP does not really provide security. Well, it kind of does against off-path attackers, but not against man-in-the-middle or on-path attackers. So to defend against on-path and man-in-the-middle attackers, we'll need some higher level protocol to help us. And the higher level protocol is what I'm going to show you in about 5 minutes. We're going to use cryptography to solve this problem. We're going to encrypt the data and use the message authentication code and signatures and public key cryptography and all the stuff we taught you. And that'll finally solve these problems that we keep saying some higher layer has to deal with. I wanted to mention beyond TCP, there's another alternative to TCP called UDP, which basically is like a version of TCP that has port numbers, but it doesn't have all the other features. There's no sequence numbers, there's no resending, there's no reliability, there's nothing to prevent reordering, none of that. So it's supposed to be like really fast if you want to like send video data, and if a frame of video doesn't make it through, don't bother resending it, just send the next frame of video. Just send, never retry. So that's UDP. UDP is a lot easier to attack because there's no sequence numbers. So it's totally insecure, even against off-path attackers. And so basically almost nobody uses it now. Okay, so I am going to switch over now to talking about how we solve all of these problems with cryptography. Does anyone have any questions before I do? All right, so I'm going to tell you about TLS. TLS stands for Transport Layer Security, and this is an application layer protocol, usually implemented in applications, on top of all these other networking layers that does provide security against all these threats, including man-in-the-middle attackers, by using the cryptographic tools we've seen in this class. Super widely used. If you go to a website and it has HTTPS, then all of the traffic is encrypted with TLS. That's what HTTPS is, TLS for HTTP. Okay, so it is implemented on top of TCP. So what that means is the application encrypts data with TLS, and then that encrypted data is sent in a TCP packet. So you would have a TCP IP packet whose payload, whose data is some TLS encrypted stuff. Okay. So TLS also provides this byte stream abstraction that's reliable, in order, and so on, but now has additionally security against adversaries. On path, off path, man in the middle, eavesdropping, modification, defends against all of that. Okay, so it's going to try to prevent eavesdropping. It's going to try to prevent attackers from modifying the data, and also going to prevent replay attacks, where an old message that was sent once is replayed and now the recipient thinks it was sent twice. Prevents against that too. And also provides authentication. When you make in your browser, go to a website with HTTPS, TLS protocol will authenticate that you're talking to the server that you meant to talk to. Authenticates the server using public key cryptography. So it's great. It's a great example of the cryptography tools we showed you here. You can understand all of it, and it's super widely used. Over 95% of all web connections are protected with TLS, I think. So let me tell you how TLS works. I'm just going to dive right immediately into the details, all the nitty gritty. When you make a connection that is protected with TLS, first TLS does some setup. And the setup involves sending messages back and forth to establish keys and synchronize state and all that stuff. So TCP had that three-way handshake. TLS has more than three back and forths to set up a secure connection. We're going to assume that a TCP connection has already been established. So first you do the three-way handshake to set up a TCP connection, which you can send all these TLS messages over. So the first step is the client sends a message called the client hello message, which basically tells the server, I want to start a TLS connection with you, please. And the client provides a list of the encryption algorithms and message authentication algorithms it supports. And it also provides a random number, a nonce, a random 256-bit number picked by the client. And then the server responds with a server hello, the server hello, the server picks an algorithm that both the client and the server support. AES CBC encryption with SHA-256 HMAC, and we're going to use the following Diffie-Hellman. And the server also has its own random number, a nonce, that it sends. The purpose of these random numbers are to prevent replays. They are going to be different because they're random. If you pick a new random number in a new connection, it'll be different than the random number in the previous connection. So this is going to prevent an attacker who eavesdrop on a TLS connection and observes the data in one connection from resending that data to the server. An attacker can try to do that, but because the random numbers will be different, the server will be able to detect, whoa, something's not right here. Because in the first connection, the server picked random number R. In the second connection, it picked random number R prime. If the attacker is replaying stuff from the first connection into the second connection, and like it's mentioning R instead of R prime, the server's like, whoa, that's wrong. It should be mentioning R prime. Basically, that's the intuition. Okay. So if I connect to my bank and like send a network request that causes my bank to do bill pay to transfer, $500 on my credit card, an eavesdropper who records that and then resends that to the bank will not be accepted the second time and cause a second transfer to happen. Okay. Then the next thing that happens is the server sends its certificate. We're going to use public key cryptography to set up a shared key between the client and the server is going to authenticate itself. So the client's going to need to know the server's public key. So the first thing, the thing that the server does at this step is the server sends its public key and sends a certificate so the client can verify that that's the correct public key for this server. Okay, so the client might be my web browser, and I might have typed into my web browser Amazon.com. So my browser is connecting to the web server, and the web server sends back a certificate that says, here's the public key to use, and a certificate that's signed that says, that's the correct public key for Amazon.com. So my browser checks, is the signature on the certificate valid? Yeah, okay, good. Is that a certificate for Amazon.com, the website that I wanted to go to? Yeah, okay, good. Okay, I can use that public key in the certificate. Okay. Now, this doesn't yet prove that the client is talking to the legitimate server, because certificates are public. An imposter could send Amazon's certificate. So we need some additional steps to make sure that the client is talking to the legitimate server, to actual Amazon, not just someone else who knows Amazon's certificate. Someone else who's trying to be an imposter will not know Amazon's private key. So what happens now is going to have to involve Amazon's private key. So the next step is that the client and the server are going to they're going to obtain a symmetric key that they can use for this connection, for encryption and message authentication. That is kind of like two purposes for that. One purpose is they need a symmetric key, a shared secret that they can use for encryption and message authentication. The other purpose, it's kind of an implicit purpose, is the process of establishing this shared key is going to prove that the client is talking to the real server, not an imposter, along the way. Because that process is going to involve the server's private key, and the imposter doesn't know the server's private key. So the imposter won't be able to complete this process. Okay. And this process works. It's Diffie-Hellman. So I showed you Diffie-Hellman. That's what TLS uses. The server picks A, it computes G to the A mod P and sends that to the client. The client picks B and sends G to the B mod P to the server. And then to verify the identity of the server computes a digital signature on the message and sends a digital signature on the message. That could only be computed by the real server. So the client can verify that this G to the A message came from the real server, not from imposter. Then Diffie-Hellman tells us how both sides can obtain a shared secret. G to the AB mod P. That we call that the pre-master secret. I don't know. There's a whole bunch of shared secrets, so we give them some crazy things. The property of Diffie-Hellman is that an attacker who's eavesdropping can't figure out what this shared key is. And an imposter who's trying to pretend to be Amazon won't be able to send this digital signature, so they also won't be able to participate in this actively. So the imposter will only be able to eavesdrop, but an eavesdropper can't figure out the shared secret. What's that? Oh. Oh, I hope we make it. Okay. If we don't make it, I'll freestyle it. And oh boy, I feel bad for everybody recording. What's that? Do you have a charger? Ooh, thank you. I should have brought mine. Thank you so much. Okay, I'll keep going. Then once they have a shared key, the pre-master secret, they derive a bunch of other shared keys from that. They need to use shared keys to use for encryption and for message authentication. And you might remember in project 2 that we said it's a good design principle to use a different key for encryption than you use for message authentication. So we need a separate key for encryption and for message authentication. And also it's a good idea to use a different key in each direction. So we actually have 4 keys. 2 encryption keys, 1 in each direction, 2 message authentication, 1 in each direction. Okay, those are derived from the pre-master secret by hashing or seeding a pseudorandom number generator. And crucially, they're derived not just from the pre-master secret, but also as a function of these random numbers that were initially picked. So you might think if an attacker were to resend data from an old session, like the same G to the B or something, maybe you'd get the same pre-master secret, but it would be a different random value on it for a new connection. And so you'd end up with different shared keys, and an attacker who doesn't know the pre-master secret wouldn't be able to predict what the new shared keys are. And because they're different shared keys, the message authentication codes from the replayed connection would no longer be valid on the new one. Oh my gosh, I am sure that made no sense. I'm so sorry. I wish I knew a better way to explain it. But if you want, you can go try thinking on your own about what would happen if an attacker tried to replay messages from a previous connection to the server and try to resend old stuff without knowing what the shared keys of the pre-master secret was. And I think you'll discover that the attacker can't compute the correct keys for the new session, and the keys for the new session are different because they depend on the server's RB, which is different. And as a result, the attacker can't figure out the correct message authentication codes to make the replay work. So replays will be rejected. Oof, that was a lot. Okay, then the next step is each side proves to the other its identity and that it was participating and so on by taking all the data that was sent so far and computing a message authentication code on that with the MAC keys that were just derived. So an eavesdropper will not be able to derive the pre-master secret, and so cannot derive the MAC keys, and so therefore cannot compute a correct MAC. And this turns out to provide like very strong security against some active man in the middle who's like modifying individual messages in the handshake. If an attacker tries to modify any message, then the MAC will not be valid, and they'll be able to detect that someone was tampering with things. So this does double duty of like both sides kind of like authenticate each other that they're participating. The server proves this not an imposter. And also it's a way they can verify that nobody was modifying any of the data exchanged in any of these previous messages. And then you're done. Now they have keys and they can encrypt and apply a MAC to their keys. And what TLS does is it applies a MAC to the data and then it encrypts that with symmetric keys. Because now all the MAC and encryption is done with a symmetric key, it's very fast. That's TLS. So before I talk you through like the implications of this design, any questions? Yeah? Good. Suppose the attacker hijacks this TCP connection. Where in this sequence of steps is it get detected? Yeah. Would you like the attacker to pretend to be a client or pretend to be a server? Server. Okay. The client is my web browser, is connecting to Amazon. The attacker is trying to pretend to be Amazon. Good? That's the next slide. So let me talk you through why an imposter can't pretend to be Amazon. What goes wrong in this process? If the attacker tries to, if I'm talking to the imposter and the messages like allegedly from the server are actually coming from the imposter, the imposter is gonna be unable to send that signed message because the imposter doesn't know Amazon's private key and so cannot sign a message with G to the B. So the imposter's attempt is going to fail right there if they're the ones sending all the messages allegedly from the server. Okay, then it won't, and the client will immediately detect invalid digital signature, something's wrong, shut down the connection. The other strategy that an imposter might try to do would be to be a man in the middle. So my browser really is talking to Amazon, but the man in the middle is modifying data in these connections somehow. I don't know, modifying some of these messages. It's not clear what the attacker would modify, but yeah, I don't know really what the opportunity is, but I can't think of an attack. But anyway, if they were a man in the middle and they tried to modify some of these handshake messages, the step where the MACs get exchanged, the MAC would be invalid because let's say the attacker modifies something in a message from the client, the G to the B message from the client. I don't know why that would help the attacker, but let's say they did. Then what the client sent is different from, yeah, that doesn't even make sense, does it? Let's say the attacker modifies the server hello message. When a man in the middle attack who's modifying the server hello message, then what Amazon sent differs from what my web browser received. When the Amazon computes a MAC on all of the handshake messages, it's going to send me a MAC on all the handshake messages it sent. My browser is going to compute a MAC on all the handshake messages it received. Because the attacker modified some of those, what was received was different from what was sent. So the MAC my browser is expecting is different from what the server sent. And so therefore my browser will detect when those MACs are exchanged that something has gone terribly awry. And it will call the whole thing off, shut down the connection, not allow any data to be sent. So the simple case is where the attacker pretends to be Amazon and then they cannot send a digitally signed message, so they just get blocked right there. And the complicated case is a man in the middle who's trying to do some crazy thing about modifying messages, and they get blocked by the message authentication exchange at the end. Did I lose you? Are we good? This is a detail. You can take it on faith from me. It is okay to take it on faith from me that this is secure against man-in-the-middle attacks and secure against people who try to pretend to be the server. Okay. So in this communication, the server is authenticated. My web browser can know it's talking to Amazon. Yes or no? Is the client authenticated? Does Amazon know which client it's talking to? No. Okay. Why not? We did all this cryptography.
Or like your session key that you made from client to the server is a key check. So if someone like put their own session key given that you've like gone into them and then send it to Amazon. So now you've created your own map or you create your own force symmetric key given your own like Giga and Maki instead of Giga Maki. So then Amazon is just sending data encrypted and mapped from that location.
I got you, but I'm gonna simplify you a little bit. Oh, do you want to take another stab at it?
The server does not know like what the into the client.
Yeah. Just to repeat what you said, the client isn't registered with a certificate authority, so there's no like way for the server to identify who the client is. Another way to say that is the server in this exchange here has a private key that's using to digitally sign some stuff. And a matching certificate to go with that private key. The client doesn't have a private key and doesn't have a certificate. The client isn't signing anything. So the server has no way to verify what client is connecting. Anyone could be connecting. And in some sense, that's the intended, like by design, Amazon wants anyone to be able to connect to them. If I had a private key on my machine and I had a certificate for it, then we could modify this to for the client to digitally sign some message, and then the client could be authenticated. But the basic, and that is an optional variant, but the basic protocol does not involve that. So at the end of this, the client knows it's talking to Amazon, knows it's talking to the right server. The server doesn't know who the client is. The server doesn't know who it's talking to. It could be anyone. It's got a secure connection to someone. So if Amazon needs to know which user this is, what account to use, what do? Yeah? Cookie tokens, username, password. The client has to send like username, password, or session cookies over this TLS connection. And then if the client sends the right username, password, or a valid session cookie, then Amazon can know who the client is. So we use the standard existing web authentication mechanisms to authenticate the client if that's needed. TLS doesn't provide that by default. Yeah. Exactly. Anyone can access the Amazon homepage even without logging in. You can open a private browsing window and connect to https://amazon.com, and you'll have a connection there to there. But then their web server will insist that you have to log in before allowing you to like buy something, right? Or enter a credit card number or something. And that's the logic of their web server. It's not part of TLS. Yep. Every HTTPS website. Every HTTPS website has a certificate. It has to. That's part of the requirements for HTTPS. Yeah. It all goes on under the covers when you connect to a website by HTTPS. Yep. This TLS three-way handshake. I'm sorry, the TCP three-way handshake, and then this TLS setup, and then the data being encrypted in message authentication code. Yep. Yeah, yeah. How much computation? There's computation and there's latency, delay. The computation is primarily the public key cryptography, the Diffie-Hellman. And a Diffie-Hellman might take a millisecond. So it could be more than that on a phone. It could be like on a slower processor, it could be 10 milliseconds. So it's a non-trivial amount of computation. On the server, it's probably faster. And high-end servers will actually have hardware accelerators for that. So there's some cost, but it's not a big deal for most servers. And then the symmetric key cryptography is so fast that you might as well ignore it, the cost of it. You can encrypt and a computer message authentication code an order of magnitude, 2 orders of magnitude faster than your network. So that's basically free. And then there's latency. This back and forth setup handshake involves sending a message and then waiting for a response, and then sending a message and waiting for a response. And if it takes 50 milliseconds or 100 milliseconds to get to the server, I might have to do 4 times that delay before can start receiving any of the web page, any of the HTML of the web page. So it can cause a delay for the page to load of 100, 200, 300 milliseconds that is driven by the time, the round trip time to send a packet to the server and get a response back. And if the server's on the other side of the world, the speed of light might mean that that could be 100, 200 milliseconds round trip time. If it goes by satellite, it could be 500 milliseconds. So that could be noticeable. So what most many websites do is they have many locations around the world, and they have a way so that automatically the connection goes to a nearby server, so that, you know, you're connecting to a server within a few thousand miles of you, so the time of like delay is not too much, so the latency is not too much, so you don't notice the delay while the page loads and connects for the first time. And also, this only applies the first time your browser connects to Amazon. Then subsequent connections will like reuse that same connection for a while. Yeah. So when TLS was first introduced, the computational costs were significant, and many websites didn't use it because it was too expensive, and now it's basically free. Almost. So almost everyone uses it. All right. TLS defends against replay attacks. I kind of talked about that before. TLS also prevents replaying these data packets. When the client sends some data in a packet, it's encrypted and there's a message authentication code. An observer who eavesdrops on that cannot send a copy of that same data a second time, because there's a unique index in each one of these messages. It's called a record number in TLS. It's your idea of index. 1, 2, 3, 4, well, 0, 1, 2, 3, 4. Each message sent has one higher record number. They are included in the M. So they're included in the part that is encrypted and has a message authentication code applied, so an attacker can't modify them. And the recipient checks to make sure that they arrive in order. Should be 0, 1, 2, 3, 4, 5, 6. Should be nothing out of order, because TCP takes care of out of order. So this prevents replay. A kind of handy thing about TLS, it provides forward secrecy. So if today some eavesdropper records the encrypted communication can't decrypt it because can't break Diffie-Hellman, can't break AES, but just records the ciphertext. Let's say a year from now, the attacker figures out how to hack into the server or how to hack into the client machine and is able to get like private keys or whatever data is stored on the machine. There'll be nothing stored there that allows decrypting old sessions because the pre-master secret and the symmetric keys get deleted at the end of each connection. And the signing key doesn't help to like figure out what the Diffie-Hellman thing must have been. So that's kind of a nice like robustness property. Today, everyone uses TLS 1.3 that has some slight improvements over what I've shown here. I showed you this scheme with a couple of back and forths. It turns out the G to the B mod P message can actually be sent right at the very start. Doesn't depend on anything before it. And so it can be sent right after the client hello. And then anytime someone is sending two messages right after each other, they can be coalesced. So the G to the B can be included in the client hello. So that actually reduces half a round trip time, or reduces the latency just a little bit. All right, so TLS is basically the answer to all of our network security woes. It defends against the man-in-the-middle attackers and on-path attackers and off-path attackers. A nice thing about it is it's like called end-to-end security, meaning my web browser does the encryption, Amazon's web server does the decryption. And so we don't have to trust any router that is handling the data. And we don't have to trust like the TCP IP software in my operating system, because those are only handling encrypted data. And so even if they're buggy or if they're malicious or they're hacked, they can't do anything to the encrypted data. Okay, so if we're using TLS, that stops most of these attacks we've seen so far. ARP poisoning, DHCP spoofing, TCP injection, TCP connection spoofing, all that stuff gets stopped by TLS. Yeah, and just to say it again, why can a man in the middle, why is a man in the middle stuck? A man in the middle can observe G to the A mod P and observe G to the B mod P, but they can't figure out the Diffie-Hellman shared secret, the G to the AB. This is because of Diffie-Hellman, the magic of Diffie-Hellman. So thank you, Diffie. Thank you, Martin Hellman. We appreciate you. One thing that TLS does not provide is it doesn't provide anonymity. If you want to conceal your identity, TLS isn't it. Okay, so if you are a human rights activist working in a country with a repressive regime and you're documenting corruption or abuses by the government, beware, TLS is not going to protect your identity. If you're a whistleblower and you want to contact the New York Times with a big scoop and leak some data, TLS does not protect your identity. Even though it's encrypting the data, it's not encrypting your identity. And the reason is because it's this application layer. Encryption is done in the application. And then this encrypted data is sent in a TCP IP packet. That TCP IP packet has in the IP header an IP source address, your IP address. So that is partial information that could be used to link back to your identity, maybe. It also reveals what web server is being connected to if you're using HTTPS, because the TCP IP packets in that header have the destination IP address, and that's the IP address of the server. And actually, the certificate contains the server's domain name, and the certificate has to be sent in the clear as well, unencrypted in that setup. So an eavesdropper can see the domain name of the server, so it can see that I'm trying to connect to Amazon.com. So if I'm trying to keep secret what websites I'm connecting to, TLS isn't going to do it. HTTP has the very same vulnerabilities. Neither of them are anonymous. HTTP is web connection over TCP without the TLS. HTTP and HTTPS are the same. The only difference is that with HTTPS, we use TLS. With HTTP, we don't. So in either case, there's a TCP IP header with source addresses and destination addresses. Yep.
And I guess this is what like is so benefit that of VPN is that it hides all of this information into that location.
Yeah.
And is it also encrypt like what's the word credentials as well or studios? Like you said that the domain name was like it was like it was there. Does it also hide that? So like hide this entire response?
VPNs, yeah. Okay, suppose I do want to protect against this. Protect some anonymity, or I don't want my ISP to see what websites I'm visiting. A VPN could be an answer there. And let me tell you about how that works. But I suggest we take a 2-minute like stretch break before we do that, because we've been going a long time. So like just 2-minute meditation, stretch it out. No kidding. This is crazy.
How can you teach for 3 hours straight? This is for 3 hours straight. That's 15 minutes. Yeah. There. Anything. Yeah, it's definitely.
Of course. Okay, VPNs. VPNs. So let me pick an example scenario. Hey, Zoom folks, are you still there, or can you still hear me? You want to unmute and tell me if we're good? Did I lose you along the way?
Yes.
Yes. Okay, VPNs. All right, I'm going on a tangent here. We're taking a left turn, but I love it. Thank you. No. Blue background. Let's suppose that I'm getting ready to go to like a protesting ICE. And I go to this forum like, disruptice.org or something like that, where we're like making our plans. And we're going to go to the protest. And then I'm like, oh, what if something happens at the protest and my ISP gets subpoenaed? And like, even though I'm going to https disruptice.org, my ISP has records that they assign such and such IP address to me. And they might have records that I opened this TCP connection to that IP address at this time. And so their records might reveal the IP addresses of all of their customers that went to disruptice.org, even if all those connections were over HTTPS, right? ISP knows what websites you're visiting. And if they're recording that, which they very well might be, then they could be subject to a subpoena after the fact. Suppose that I decide that is not within my risk tolerance. I am not comfortable with that. What can I do about that? One answer could be a VPN. So how does a VPN work? I pay $10 to some company somewhere in the world, WeHideYourStuff.com. Except maybe it's not stuff, but okay, WeHideYourStuff.com. I open a TCP connection and a TLS connection to WeHideYourStuff.com server. Okay. And then when I want to visit disruptice.org, I have my browser, instead of sending that connection request to disruptice.org, send it to WeHideYourStuff.com in Bermuda, encrypted with in this TLS connection to WeHideYourStuff.com. So it's encrypted. And then when WeHideYourStuff.com receives that, it decrypts and it sees, oh, there's a request to connect to disruptice.org. And they connect to disruptice.org, not me. So what does my ISP see if I do this? What my internet service provider, what do they observe? Yeah? A bunch of connections from my machine to hidemystuff.com. Yeah. They probably won't even see if I've chosen the VPN well, they probably won't even see the connections that Hide My Stuff made to disrupt ICE, because Hide My Stuff probably has their own ISP in Bermuda or something. And if I chose it to be one outside the US, maybe it's not so easy to subpoena them for their records. So my internet service provider doesn't know anything except that I'm making a VPN connection, but they don't know what I'm doing with that VPN connection. And the VPN knows, so I have to trust them to keep it secret. But if I've chosen them well, maybe they're in a country that's like not going to accept US subpoenas, and maybe I chose them so they're not going to keep records. So if they get a subpoena, they won't have any data. That's the idea of a VPN. So a VPN is just TLS, except you have two TLS. It's crazy. There's a TLS between me and the VPN. And then I form a TLS from my browser to the forum, but it doesn't go direct from my browser to the forum. It goes by way of the VPN and then onto the forum. Through that encrypted, it's called encrypted tunnel. So to send some data to the forum, my browser opens a TLS connection with that forum, and then everything is encrypted with a key that only the forum knows, right? So it got TLS ciphertext that the forum can decrypt. Because it's end-to-end security, it doesn't matter how those ciphertexts are communicated. I can get them to the forum in any way I want. It'll still be secure. I could use carrier pigeon. So the way that I do it is I take those ciphertexts and I send them to my VPN company, encrypted in the TLS connection that I made with the VPN company, and have them send it onto the forum. It's like using my VPN as a router. So it's like now double encrypted Not because that provides extra security, but just to hide from my ISP so that my ISP no longer sees the IP addresses of what websites I'm visiting. Yeah.
Go back to that same time. So would it-
And then the responses come back the same way. Yeah. Yep. So then people try to use VPN so that the Great Firewall of China cannot see their data. Mostly not, because the people running the Great Firewall of China are knowledgeable technical people who go map all the VPNs that you're likely to be able to buy commercially and keep track of all their IP addresses and block all of them. But it depends what VPN company you have. Not so, I think maybe if you're sophisticated enough, you can, but if you try the most popular VPNs, you get blocked or something. I'm not sure. This is what I've heard. I don't have firsthand experience. And they do some amazing, crazy stuff. Like if you open an SSH connection to try to use that to form a VPN, they have some special detection of SSH sessions with machine learning and so on. So there's pretty sophisticated stuff. So that's a VPN. One thing you might notice is that the VPN knows that I am going to disrupt ice.com. So I got to have full trust in the VPN. And so this is a big question with picking a VPN is how do you know whether they're trusted or not? Whether to trust them. If like the NSA wanted to spy on people who have really sensitive stuff, a great way to do it would be for them to form a VPN, the most secure VPN ever.com. Advertise, we're super cheap and we have the highest security ever, and then keep records on what everyone is doing through their VPN. So it's kind of a conundrum how to pick a VPN. Yeah.
Where like the Chinese government will like ban one VPN and you will find another one. And they'll go with that one. And of course, like I think what we ended up doing was we had like one that like a friend had just set up on our own computer.
Yeah.
Like in the US. So
Yeah.
we could connect to that one. But yeah, it's like they just like changed it.
I see. They're maintaining a list of VPNs that are blocked, and then some new VPN becomes available and word of mouth, it gets around. This is the one that hasn't been blocked yet. Use that, and it works for a little while, and then it gets blocked. Okay. Our cat and mouse game, arms race. Are VPNs used in military? I don't know. Maybe. I don't know very much about what the military does. Yeah. Yeah. Yes, shadow socks. Okay, so suppose we do want anonymity. And maybe I'm not sure that I want to trust a VPN either, because that sounds like a lot. Then there are sophisticated technical solutions, and I think maybe like in maybe the last week or something, I'll tell you about them. One of the very cool systems out there is called Tor, that uses multiple nested TLS connections and all sorts of cool cryptography to like actually provide strong anonymity. But it takes a little bit of doing. Yeah. Oh, as long as I'm on tangents, you want to hear another tangent about anonymity? Let's talk about anonymity of TLS. What an attacker can, an eavesdropper, what your internet service provider can know about the web browsing you're doing. Suppose you go to, this is not a test, blue background all the way. Suppose you go to Netflix and you start looking around for a movie to watch. Can they tell that, can your internet service provider tell that you're visiting Netflix? Can they tell how many hours you're spending on Netflix? Yes. Can they tell what search terms you entered into the Netflix search bar? I see a yes and a no. Okay, help me out here. Give me an argument for yes. just be the query parameters, which is sent over the network. Give me an argument for no. Yeah. If I went to Netflix over HTTPS, then they'll be sent. They're the data that is sent through TLS, so they'll be encrypted. And most major websites use HTTPS. So in practice, if you go to Netflix, you'll be using TLS. So the query parameters will be sent inside TLS. They'll be encrypted. Your internet service provider cannot see the search terms that you enter into Netflix. Okay. Can they see which web pages, which URLs on Netflix I am visiting? Yes, I see some yes and some no. Okay, good. We got another disagreement. If they're on different IP addresses, that's possible. What if they're on the same IP address?
Same port as well.
Same port as well. Then I don't think so, because the URL, the path of the web page is sent from the browser to the server. That's part of the data that is sent. All the data that is sent from the browser to the server is sent by TLS, meaning it's encrypted.
Maybe possible.
If Netflix was running 2 web servers and they had on 2 different IPs or domain names, and they had some of their pages on server 1 and some of their pages on server 2, then an attacker could tell which of those 2 servers being visited. Typically that doesn't happen, but it could happen. Like, I don't know even how it would happen. All right, let's get even more obscure. Could the attacker tell how long the URL is that I'm visiting on Netflix? Not what URL, not what page, but just the length. Ooh, okay, this is a hard one. So when my browser visits a page on Netflix, it sends some data to the Netflix web server. The data it sends is a GET request. GET space / and the path, the whole path, everything after the domain name of the URL. TLS will then encrypt that, let's say with AES encounter mode, I don't know, and then we'll append a message authentication code. Does an eavesdropper who can observe that ciphertext get to know how long the URL was? Modulo some block size, there could be some padding.
Small number probably not, but I'm looking up the limit is about like 2,000 characters. Probably 2,000 characters they can tell it's not.
So with AES counter mode, the length of the ciphertext is the length of the plain text plus a fixed constant. So with AES counter mode, someone who observes a ciphertext can tell how long the plain text is. So they could probably infer how long the URL for the page is. With CBC mode, it's padded out to a multiple of 16 bytes. So you could probably tell the length up to multiple of 16 bytes. So if Netflix had one page whose length was unique, was really different from all the other pages, they could tell if you visited that page. Your internet service provider could tell. Now here's a really crazy one, and then we'll move on to something else. Can your internet service provider, if I'm watching a movie, tell which movie I'm watching? Yeah, I don't expect you to know. This is a trick question. This is a research paper, it turns out. What are you thinking? You're going to say probably. Why? Not every movie has the same length. So the internet service provider can observe, probably tell how long the movie I watched was. But I don't know how reliable that is, because there's like, tens of thousands of movies and there's not that many lengths, and I might stop 2 minutes early before the ending. But you're right, you're onto something. Frames, you said? One thing to know about videos is that they use compression. And the compression ratio depends on the image. If it's mostly black, it gets compressed to something really short. If it's got a lot of detail, it gets this, you can't compress it very much. So it turns out that if an attacker really cared, they could go watch all the movies and record the lengths of all the packets. Each frame gets compressed separately, has a separate length, so that length can be observed even though it's encrypted. You can see the pattern of lengths, and from the pattern of lengths, uniquely identify. It's like a unique fingerprint of the movie you're watching. It's crazy. Okay, so bottom line is TLS encrypts everything. So it basically provides confidentiality, except not anonymity. And there are some leakages there. Yeah.
But aren't there servers that like where one IP maps to different servers? Like
Yes.
you'll go to like my IP, you'll play that out. This specific IP, right?
Yes.
But, like, this IP will have Amazon and also like Facebook and
Yes.
also, like, different things.
Yes.
So then does that ISP would know which IP I'm going to, not necessarily which website?
Good. Okay. This is a detail. It's not important. You don't need to know this. There are shared hosting where one IP address, one machine will host multiple websites. And the big example of that is Cloudflare. If you have a blog, a lot of people use Cloudflare. And to make it faster to access your blog, Cloudflare will host a copy of your blog on their own servers. And they have servers all around the world. They have servers in California and in New York and Texas and Canada and everywhere. And they automatically set up DNS. It's really cool. DNS resolution figures out the nearest Cloudflare server near you, gives you an IP address of the Cloudflare server near you. And then when you're going, your browser is going to that blog, it's actually going to a Cloudflare server near you so it can respond really quickly. That Cloudflare server hosts tens of thousands of blogs on it, tens of thousands of different websites. So to make that possible in TLS, the client sends the name of the domain name that it wants to connect to, and the server sends back the certificate with the domain name in it. So eavesdropper or your internet service provider sees not just IP addresses, but also the domain name in the certificate or the domain name the client sends. It's called CLI, I think. Anyway, that's way beyond what you need to know for this class. Oh my gosh, I just geeked out big time there. All right, another thing that TLS does not provide is it doesn't provide availability. Denial of service attacks are totally possible. An attacker can shut down or stop a TLS connection. Because remember, TLS data is sent over a TCP connection. An attacker can send a reset packet to shut down a TCP connection. And if they shut down the TCP connection, then no more TLS data is going to flow over that TCP connection. So what does an attacker need to know to shut down a TCP connection? They need to know the sequence numbers so they can send a reset packet with the right sequence number. So a man-in-the-middle or an on-path attacker can shut down a TLS connection by shutting down the underlying TCP connection. But an off-path attacker cannot, because an off-path attacker won't know what the TCP sequence numbers are, and so won't be able to send a reset packet with the right sequence. So this means that sensors can still censor internet traffic by connecting to an internet service provider and getting a copy of all the traffic, just eavesdropping on all the internet traffic. They could tell which websites people are going to, not what pages, but what domain names people are visiting in their browser. And if it's a domain name that they don't want to allow, then they can inject a reset packet because they're getting a copy of the data. They're an on-path attacker who could see sequence numbers, so they can send the reset packet, and they can shut down even TLS connections. TLS does not defend against this. Yep. They could be controlling the router and like adjust the router to refuse to pass any more packets through the router. It turns out for software engineering reasons, that would really slow down routers. If every time they were forwarding a packet, they had to look up and see, is this one that should be blocked or not? So in practice, sensors who do this at the scale of entire country, they eavesdrop and they inject packets, because then they don't have to modify the routers. They just have to get a copy of all the traffic. And so they don't slow down the routers. It's just an implementation detail. Okay. TLS, probably the #1 usage is for securing the web, for securing HTTP connections to a web server, but it can also be used for any other application that needs security. And it is widely used for other applications. For instance, it's used when my mail client connects to Gmail. And it's used when Gmail connects to Hotmail to forward on some email. And anything else that needs a secure connection. The nice thing about TLS is that it's been around for maybe 20 years now. Ooh, 30 actually. And it's been really well vetted. But another thing that TLS does not defend against is any of the web security vulnerabilities we talked about. Cross-site scripting, cross-site request forgery, SQL injection, any vulnerability in the web server or in your browser. TLS, of course, doesn't help with that. It's just passing data back and forth. One attack against TLS that was quite feasible for some time, and is still somewhat feasible, is SSL stripping. Okay, so let's suppose that I type into my browser window Amazon.com. For a while, for a long time, and I think possibly still today, I'm not sure, some browsers would first connect, the default is they would put HTTP : at the front of that. They would connect to HTTP://Amazon.com if I didn't type in the HTTP : And HTTP was the default, meaning no TLS. But Amazon wants security. That's no good if I'm connecting over a Wi-Fi network and then some eavesdropper, someone else on the same Wi-Fi network can eavesdrop on my credit card number, my Amazon session cookie. That's no good. Amazon wants security against that. So they have a HTTP website whose main page does just one thing. It doesn't have any content on it. It just has a code to tell your browser, not here, go to HTTPS Amazon.com. It redirects your browser to the HTTPS site using TLS. And then all the actual content is served over TLS on their HTTPS website. Okay? So that way, even though you didn't type in HTTPS into your browser, you end up getting the protection of HTTPS, of TLS, for websites that do this redirect. HTTP sends all the data between the client and the web server unencrypted. If I log in, my password goes unencrypted. If the session cookie is unencrypted. Oh yeah, it's really bad.
And in the split second between the redirect, it'll just be a dump of unencrypted data. If you check HTTP before the redirect, has that already been exposed?
That's been exposed. But fortunately, hopefully, there's nothing sensitive in that. Because you don't log in over HTTP, you don't send your session cookie over HTTP. The session cookie is only sent over HTTP. That's the idea. Yeah.
I would still think even if you have a session cookie, it's not necessarily sent first both website.
But yeah, so, okay. If Amazon didn't do anything special, it would get sent over both HTTP and HTTPS, and that would be really bad because then it would be exposed, exactly what you're worried about. So in practice, what Amazon does is for the session cookie, there's a flag, a secure flag, which says only send this cookie over HTTPS, don't send it over HTTP. Exactly to stop this problem. So then it will not get sent over the HTTP connection. And the redirect. Yeah, that's okay. So this is a clever mechanism to enable people to get the security of TLS. But it has a vulnerability against on-path attackers. Like if I'm in a coffee shop on their open Wi-Fi, and there's someone else in that Wi-Fi network that is malicious, they could do ARP or DHCP attacks and become a man in the middle, right? So now they're a man in the middle. When my browser goes to http:/amazon.com, that man in the middle can stop before that ever gets passed on to the real Amazon, send back a fake response that doesn't include the redirect, that looks like the real Amazon, but doesn't include the redirect. Or is a redirect to some other site? Also, that's also possible. So a man in the middle can force the user to stay on HTTP unless you have gone into the address bar of your browser and typed https://amazon.com. You typed HTTPS in. And so once the man in the middle forces you to stay on HTTP, if you then log in, your password is sent into clear, the attacker learns your Amazon password. It's very bad. So this is called the SSL stripping attack. And browsers are deploying defenses against this. There's a number of defenses. One defense is that if I've gone to the site in the past, it's probably in my history. And so if I type amazon.com, it'll probably autocomplete to something in the history, and in the history will be HTTPS:/. So my browser will automatically take me to the HTTPS version if I've been there before. Some browsers have had optional settings where they would change the default to be try HTTPS first, but it was opt-in, it wasn't the default. Starting next year, Chrome has announced that they're going to be HTTPS first. And so this attack, I think, will not work, I think. Another defense is that a website can say, I want to use HTTPS and only HTTPS. I want everybody to use TLS. And they set a configuration that's remembered by your browser called HSTS, HTTP Strict Transport Security. It's a setting that tells your browser, never connect to me under HTTP, only connect under HTTPS. Okay, 5 o'clock. I'm going to stop there. There's more we could say about web browsers and user interfaces, but hopefully this has given you an idea of how TLS works and how the kinds of cryptographic tools we taught you get used in practice.